Okay, so let's continue our discussion related to diode-based power supply. In the last lecture, we had seen a power supply based on a half-wave rectification using a single diode. And so the purpose of the transformer was to reduce the input sinusoid to an appropriate value to generate the required DC value over here. And the purpose of capacitor is to filter out the higher sinusoidal frequencies and generate a DC at this particular voltage here. And we had seen plots like this here. So this is the input sinusoid and this is the output that we obtain. And we saw that there is a ripple in the output, and the magnitude of the ripple can be expressed as VR equal to VM divided by the frequency of the sinusoid here, the input, and RLC here. And since VM is fixed by the application, frequency is fixed by the input, and RL is also RL may also be fixed by the application. So the only choice that we are left with is the capacitor. And to obtain a particular value of ripple voltage, then we have to choose a appropriate value of capacitor. And to reduce the ripple to a very small value, we'll have to use capacitor to a very large value. And we'll have to increase the capacitor to a very large value. Now, this problem can be partly relieved if we use a full wave rectifier. And this is the circuit that we use. We have two diodes, D1 and D2. And we have a transformer just like in the previous case, but we have a transformer with a special characteristics that its center is connected to ground. So there is, in addition to the two terminals, the two secondary terminals that are there is a center tap also, and that is connected to ground. And you'll see why this is required in order to obtain a full wave rectification. Okay, so let's see. So when this is positive here, let's say the input sinusoid, this primary, this is positive, this is negative here. So similarly in the secondary, this is positive and this is negative here. And the center tap is always connected to ground here. So what would happen is this particular diode will turn on, because note that this is positive here. And if you look at the circuit, positive here, D1 here through RL and then to the ground here. So because of this positive voltage here, and this voltage is sufficiently high compared to the diode drop that is there here. So that's why the diode D1 is on. And this is the direction in which the current would flow. It would start from here, flow here, and of course go through RL in this particular direction. Now when the voltage, when we go to the negative half here, negative half of the sinusoid, this part is negative here and this part is positive here. Center tap of course is ground. Now D2 is on and D1 is off, and the current would now flow, D2 would flow like this here, 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 and then back to the ground here or to the center tap here. So note that for the negative cycle also, the direction of the current is the same. The current is always flowing, whether we look at the positive cycle or we look at the negative cycle. The current is always flowing in this particular direction. And the voltage V0, if we assume that the diode drop to be negligible here, the voltage V0 will be nothing but the voltage at this particular node here, right? So which is equal to the negative part here, right? So this is what we obtain. So this is the input sinusoid here in black, and in red is what we have shown as the output here at this particular point here. And so this is what we call as full wave rectification. And so the V0 is basically following the value here at this particular point here between these two nodes here, and except for the diode drop here. And in the negative cycle, D2 is conducting and resulting in something similar to be happening here. Now the advantage of, one of the advantages of full wave rectification is with respect to the ripple that we talked about. Now in the previous case, what happened was the ripple, we'll compare the two cases, this thing here. So we note that what will happen is when D1 is conducting, the capacitor will charge up. This is what is happening here. Capacitor will charge up. And once the voltage goes below the output voltage here, the diode is off, and D2 is off anyway. In the positive cycle here, D2 is off, so the capacitor discharges through RL. Now the capacitor discharges through RL till what happens is this part here, till this particular diode. Note that in the negative cycle this part is positive, so this part is positive here, and once this part of the circuit turns on, and it charges the capacitor here. So during this particular part here, the capacitor had discharged a little bit, and therefore the D2 then charges the capacitor here. So we see this part here coming here, and then back again, then D1 comes into picture and D1 charges. So what we see here is that the capacitor is not discharging for the full period here. Capacitor is only discharging for half the period here, and therefore the ripple that we had derived here, Vm T1 by RLC, and T1 was equal to the total time period. Now T1 is nothing but equal to T by 2 here. All right, so basically in each half cycle here, this diode, in one half cycle this diode turns on, and the other half cycle this diode turns on here, and so the capacitor discharges only for about half the cycle here, and then whatever charge the capacitor has lost, then D2 turns on and supplies that particular charge here, right? So the ripple for if for same RL, same C, everything is same, the ripple is reduced by a factor of 2. So VR we can write T, if we replace T by F, so VR equal to Vm by 2F RLC here, right? So let's compare the two. So half wave rectification, VR was Vm F RLC here. Full wave rectification, VR equal to Vm 2F RLC here. And you can see the comparison here. So in black again we have the sinusoid, input sinusoid. In yellow we have shown the half wave rectification. So the diode charges up here, and since there's only one diode, so this keeps on discharging for almost for the entire period till the input rises greater than the output voltage here, and then the diode turns on, and that happens here. While in this particular case we have two diodes, and each one of them is on in this one in positive cycle and this one in negative cycle. So note that what is happening is that the capacitor is only discharging till here, till diode D2 turns on, and then it charges up again and then discharges again. So that's the reason why we are saying the ripple is nothing but the difference between this maximum and this minimum here. So the ripple is smaller in full wave rectification with the full wave rectifier. But of course the price that you have to pay for this is an extra diode and a special transformer with a center tap like this here. The diode currents are similar in full wave rectification. So we'll have note that this is the in purple here is D1. So initially, of course, when the capacitor is not charged, so you need more diode current to charge up the capacitor from 0 to the output value here. So this is there. And then in the negative cycle, D2 turns on, so the D2 current is here. And then in the positive cycle, D1 is there. So alternatively, we have D1, D2 diode currents, which are charging up the capacitor and basically replenishing the charge that the capacitor loses through discharge through RL here. And we had derived this particular expression for ID max, so this is still true. So we'll not go into full derivation again, but this equation is still true. ID average is Vm by 2RL, because note that the total current that the load has is V0 by RL here, or Vm by RL here, and half the current this diode is supplying and half the current this particular diode is supplying here, right? And so ID average is Vm by 2RL, ID max is this particular expression here. And so one of the problems with this particular circuit is as we said, that it requires a transformer with the center tap, And an alternative way of building a full wave rectification is through what we call as a bridge rectifier. A bridge rectifier which doesn't require a transformer with the center tap. So a normal transformer could be used to generate this signal here. And then let's see how this bridge rectifier acts here. So note that, okay, so let's see, this is positive and this is negative, let's say here. So what will happen is this will cause a current to flow. The current would flow through D1. D1 is forward biased, the current comes here. Of course, it cannot flow in this particular direction here, so it flows here through RL, comes here, and flows through D3 here, and comes here, and then goes back here. So that's how the circuit is completed. Note the direction of the current here through RL. So V0 is positive with respect to ground here, when this is positive here. So let's now look at when the polarity reverses. So this goes negative and this goes positive here. So now the current starts from here, goes through here. Of course, it cannot go through D3, so it goes through D2. Goes through D2 here, comes here. Cannot go through D1 here. That would be reverse bias diode here. So it goes through here, RL here. And then once it comes here, goes through here, D4, and comes back and returns back to the supply here. So note again that even though the polarity has reversed, which means we are in the negative cycle of the sinusoid, the voltage is still positive. The current flowing through RL is still in this direction and the voltage is still positive. So we are getting a full wave rectifier here. And to make a complete power supply, so what we can do is we can take RL and we can connect a capacitor across it, and we'll get the a complete power supply here. So this one will give a full wave rectification, and with the capacitor again we'll get a similar kind here with the ripple given by same expression. We have ripple voltage equal to Vm by 2f RLC here, right? So during positive cycle here, one particular path is active, and in the negative cycle the other particular path is active here. Okay, and each path consists of two diodes here. So we had seen earlier that in general we want a very small ripple, we want a perfect DC, and to reduce ripple to a small value we have to use a high value of capacitor, and that large value of capacitor causes a problem. This shows you capacitors of increasing value, and so small values of capacitors are small in physical size, and as the value of the capacitor increases, then the size of the capacitor also increases, and that makes the whole circuit bigger and bulky, and that's something that is not something which is desirable. And the other thing was, so capacitors are becoming large. They become large as you try to reduce ripple to a small value. And the other problem is that as you make the capacitor large, as we saw in the last lecture, then what happens is the diode is on for a very short period of time, and in that short period of time the diode has to supply all the charge that the capacitor lost to the load here, and therefore the peak value of the diode current, that becomes higher and higher. So as you increase C, ripple goes down, but the peak diode current becomes higher and higher, and that puts a stress on the diode. So you have to choose a diode which can handle that large a value of peak current here. So in this respect, what can be helpful is a Zener diode that we saw earlier. We saw that Zener diode is a special diode designed to operate in the reverse bias condition, and especially in the breakdown mode here, in this particular part here. And we had seen this particular symbol of the diode, and we said this characteristics is very, very steep, and we can approximate Zener in this particular mode here. In this particular mode, we can approximate Zener by a battery of a value Vz here. So what we see here is that Zener can act as a constant voltage drop element here. And therefore, we can see that if it's a constant voltage drop, it can be helpful in removing the ripple that we had in our DC voltage. and obtaining a very good value of output voltage here, output DC voltage here. So we can take advantage of Zener diode. And with respect to when we are using Zener diode, of course the Zener voltage is important, but we also said that there is a maximum Zener current and there's a minimum Zener current. Maximum Zener current, so that every semiconductor device, every resistor, every diode, every transistor has a maximum current rating, and if you exceed that, then the device may get damaged or not behave in the expected manner. And similarly, there's a power limit also. If you exceed the power limit, the device may get damaged again. And in case of Zener diode, there is a IZ minimum also. So you have to be away from this knee region here, so that you are in this steep region here, because we are trying to take advantage of the fact that this region is a constant voltage drop. So we don't want to be very close to this particular value here. So there is a minimum Zener current. IZ minimum is also an issue that we should be aware of. So Zener diode, of course, can be operated in forward bias or reverse biased. And in a forward bias, it acts like a normal diode. In reverse bias, well, in reverse bias, if you are not in the breakdown mode, it acts like an open circuit. But if you are in the breakdown mode in this thing, then it acts like a battery or voltage VZ here. So when we find Zener diode as a circuit element, we need to be aware of this particular picture here and decide whether it's forward bias or reverse bias. And if it's reverse bias, then is it in the blocking state or is it in the breakdown mode? So let's use the Zener diode for creating a voltage reference or a constant voltage circuit here. So suppose we have a voltage here and the voltage is variable, and it's a variable voltage, but what we want is that we want a fixed and constant voltage at this between these two pair of terminals or across the load here. And so note that just for the sake of discussion, we have taken VPS here, the supply voltage, the supply here. Note that it is this thing here, so it's varying. It's varying. You could think of as a DC plus say some kind of a ripple here. And when we apply to a properly designed circuit like this, then the Zener diode, if it's properly designed, the Zener diode will operate in the breakdown mode, and therefore the voltage across this particular element will be constant, and a constant voltage will appear across the RL here, and the constant voltage will be equal to the Zener voltage here. So this is what is shown here. Note that Zener diode is not perfect. We also saw that the steep region is not completely vertical, but it has a little bit of resistance, and that's why you see some small changes, little bit of ripple that is present there here. Okay, so in a simple case, if we ignore the resistance of the Zener diode, the small resistance of the Zener diode, then this is how the circuit would look like, and then we would get a perfect output voltage here. And depending on the value that you require here, you can choose an appropriate Zener diode. So let's use this particular circuit with the rectifier that we had, rectifier circuit that we had built here with the power supply here. So this is the power supply circuit that we had built, and we were trying to increase the value of C to reduce the ripple. But now we'll take advantage of the Zener circuit here. Zener circuit here, because that can give us a fixed voltage here with very little ripple. So what we do here is, note that here it was just a variable voltage here, and now what we'll do is we'll take this out, and instead of this one here, put this particular circuit here. Okay, so we took this out, we put this circuit here, and this load resistor is after the Zener diodes. The load resistor is over here. Okay, and RI is as it is, and so this is the circuit that we obtain here. And so the idea is that with this particular circuit, we would be able to obtain a much better DC voltage with much reduced ripple voltage here. Okay, so a properly designed circuit would then give a superior performance compared to a simple power supply circuit of this kind here. And similarly, we could do with the full wave rectifier also. So this is the part that generates the DC with the ripple. So we use that as an input to our Zener circuit here with RI, Zener diode and an RL here. Okay. So again, if properly designed, note that we have a capacitor and there may be a lot of ripple that you see here. We are not using a very large capacitor here, so there's a lot of ripple here. But the Zener diode acts as a very good filter, gives us a constant voltage drop. So you can see that the output voltage is pretty much fixed here. Okay, so the Zener diode absorbs all the changes that you see here. The Zener diode takes care of that. Okay, so let's analyze this particular, the voltage reference circuit. Let's look at how we can design an appropriate Zener voltage reference circuit using a Zener diode like this for a particular application here. Okay, so let's look at first the basic equations here. So if we look at this particular current here, the current that is flowing through this input resistance here, this is equal to VPS minus VZ. So this value is VZ here. So VPS minus VZ by RI. So that's the current that is flowing here. And this current is equal to the Zener current plus the load current, IZ plus IL here. So that's the fundamental equation. The current that is coming in from the source divides between the Zener diode and the load here. So that's the equation here. We can rewrite this particular equation in this form here. IZ equal to VPS minus VZ by RI minus IL here. And so now the issue here is in using a Zener diode is we have to make sure that the Zener diode is operating in the Zener mode, in that steep IV characteristics or in the breakdown mode. And further we have to make sure that the current through the Zener diode doesn't exceed its maximum current rating, or the power dissipation in the Zener diode doesn't become excessive. So let's calculate what is IZ max here. So the maximum current that can flow through the Zener diode, given this circuit here, will be equal to, note that VPS here is shown as a sinusoid, but think of it as a DC plus in AC here. Okay, DC plus a ripple, a sinusoidal ripple here. So the maximum value of Zener current here, as you can see from this equation, will occur when this VPS is maximum and VZ is fixed, RI is fixed in a circuit, and when load current is minimum, right? So there's a certain current that is coming in here, and what we are saying is the maximum value of Zener current would occur when this current is maximum and load current is minimum here, right? So the difference of the two will give rise to a maximum Zener current here, IZ max here. And similarly, the minimum value of Zener current, IZ min, will be equal to when this is minimum, this term is minimum, and this term is maximum here. So we are interested in minimum Zener current also because we want to stay in the breakdown mode. And if the Zener, if IZ minimum becomes too low, then our circuit will not act like a good constant voltage element here. And of course, then we can calculate PZ maximum. The maximum power dissipation will be equal to VZ into IZ maximum here. So these are the equations. So we are given a design. We can use these particular equations to see whether our design is correct or not by checking whether IZ max, IZ min, and PZ max they are reasonable with respect to the Zener diode characteristics. And so if a circuit is given with a particular Zener diode, we can go and check the characteristics of Zener diode that is given by the manufacturer using the data sheet, and then we can check IZ max, IZ min, and PZ max and see whether these values are reasonable or not. So that's for checking a particular design, whether the design is correct or not. But let's look at the alternative problem where we have to generate a design. So let's say a circuit like this is given, and we are given that the input voltage here can vary from 18 to 15.5 volts here. So this is a variable voltage here. It can vary from 18 to 15.5. Note that 18 to 15.5, so it's a variable voltage here. It's not a sinusoid, although the symbol here is used. It's not a sinusoid, it's just a variable voltage here. Okay, 18 to 15.5. And this structure of the circuit is given. And it's also given that the load current here can vary between 0 to 0.1 ampere here. Now 0 is always a load current because as many times in your circuit what can happen is that you may remove the load altogether, and so IL equal to 0 is always a condition that we should consider, and IL maximum depends on the application here. So in this case IL will go from 0 to 0.1 amperes, and input is varying from 18 to 15.5 volt here. Input is varying between these, and we have to design this particular circuit, which means we have to determine a suitable value of Ri, and we have to determine the specifications of the Zener, or we have to determine the currents and voltages associated with Zener so that we can select a appropriate Zener diode here. So these are the equations that are there here. Basically these equations, Iz max and Iz min here. And our problem is, as I said, that our problem is that we want to remain in this vertical region here. We want to remain in this particular region here and away from the knee here. And we don't want to go to excessive Zener current also to avoid damaging the Zener diode here. So the issue here before us is we have given VPS max, we are given VPS min here. And since we want an output voltage of 12 volts, so selection of VZ is easy. We want VZ equal to 12 volt here. So that's not a problem here. The issue before us is how to choose Ri. And how to choose Ri, because if we choose an Ri of a particular value, it will result in particular value of Iz max and Iz min. And those values may be realistic or unrealistic depending on how we have chosen Ri. As an example, if I choose Ri equal to 40 ohm. Now if I choose Ri equal to 40 ohm, since we are given VPS max and IL min and everything given, we find Iz max is 0.15 amperes and Iz min is minus 0.013 ampere here. And so Iz max is not an issue. But Iz min, note the direction of Iz. Iz we have already taken as a reverse current. And when Iz min is minus of that, it means that the current is going opposite direction here, which means that the Zener diode is not reverse biased. And our condition is that Zener diode should be not only reverse biased, but it should be in this condition here. So the choice of Ri equal to 40 ohm is not right here. We will not be we will not be in this vertical region here. So at a certain value of VPS, we'll go somewhere here. We'll go in this particular region, and therefore our device will not work properly here. So 40 ohm is not a good value. Similarly, suppose I choose Ri equal to 10 ohms. Now if I choose Ri equal to 10 ohms, then Iz max is 0.6 amperes. We can calculate from this equation. Iz min is 0.25 amperes here. So looks like okay, except that note that this is also a bad design. 0.6 amperes would be somewhere here, 0.25 would be somewhere here. So we are okay, we are in the steep region here. But note that it's a bad design because our circuit is being designed to handle maximum current of 0.1 ampere here. And for 0.1 ampere here, we are wanting the Zener current to be as large as 0.6 amperes here. So we are unnecessarily passing a lot of current through the Zener. And a lot of current through the Zener would also result in a lot of dissipation in the Zener. And we'll have to choose a Zener with a higher current rating, with a higher power dissipation rating, and that would make the Zener a costlier diode. And this is not something which is really needed when the currents in the circuits are only 0.1 ampere here. So we need to use a appropriate value somewhere. We can see that 40 ohms is too large and 10 ohms is too small. So we need to use somewhere in the middle an appropriate value. And so one way in which we could do that is the following. We want Iz max to be somewhere here, but we don't want Iz max to be very large. And we want Iz min to be away from this particular region. And so we want Iz min to be positive. So one thing we can do is we can take the ratio of Iz max by Iz min equal to 10. And if we do that, that would make sure that it would make Iz min positive here, and therefore we are away from this particular knee region here. And Iz max also will not be very, very large compared to this. So if we use this Iz max by Iz min ratio as 10 here, then we can, from this particular equation, we can derive a value of Ri here. Given by this, just taking a ratio and rearranging, we'll get Vps max minus this one here. And in deriving this equation, we have taken IL min equal to 0. So even if the problem gives you IL min which is not 0, let's say IL min was 0.01 ampere, but we should still design for IL min equal to 0, because it can always happen that nothing is connected to our RL, to our load here, and nothing is connected here, or the load is removed, and in that case we should make sure that the Zener current is not excessive, and while it's the rating of the our Zener diode here. So we'll take IL, whatever IL min is given, we'll still take it as 0 here, and so we can choose Ri in this particular manner here. And once we get Ri, we choose in this particular manner here, we'll get Iz max, we'll get Iz min, of course, and we can also calculate Pz max here. And so we'll have these values, Iz max, Iz min, and Pz max. And based on these values, we can go ahead and select a appropriate Zener diode for our application here. So let's do the design here. So for this one, Ri will turn out to be, if we plug in the values, 29 ohms, and Iz max is 0.207 amperes, Iz min is 0.0207 amperes here, and Pz max is 2.48 amperes here. And note that the current that is required is 0.1 ampere was the load current, maximum load current here. Iz max is 0.2, so it's not excessive like 0.6 that we had calculated earlier. And Iz min is also 0.02, so it's a small value here, but still positive. And so these note that this design was based on Iz max by Iz min equal to 10, and that ratio is something that we can alter. We can alter that particular ratio and obtain different designs that are there. But for this particular course and for our discussion, we'll take a suitable value of ratio Iz max by Iz min equal to 10. Note that in many of the designs, often we find that the number of equations are not sufficient to obtain an answer, and the number of equations may be, number of constraints on the problem may be less compared to number of the parameters that you have to determine, and then you have to use other criteria to obtain the values of the parameters. And in this case, we've chosen a criteria that the ratio of Iz max and Iz min is equal to 10, and we've taken that as an appropriate value and used that to calculate the value of Ri, and use that to determine the proper Zener diode for a particular application here. And if we had taken a more detailed model of Zener diode, then we would have taken the Zener resistance also into account here, and we can do a more realistic and more, but it would become a slightly more complex design. And but this is an initial design that we can obtain by following this particular method. And as we discussed, that we can take an initial design and then we can simulate it, and some fine-tuning we can do based on the results of the simulations. So after determining Ri like this, and after choosing a Zener diode, one can go ahead and simulate the circuit and evaluate the results, and based on that, one finds that this Iz max is unnecessarily maybe too large, 0.207. We can tweak the value of Ri. Maybe we can increase Ri, and that would result in smaller values of Iz max here. but it would result in smaller value of IZ min, and we have to make sure that we are in the safe zone here. So based on the selected diode, we can then fine tune the values of Ri. Okay, so let's stop here.